Hi all. So we are moving to the final regular track session of ISEC 2024. So here we have one short paper and one regular paper. So first we have Sajid Sarwar here to present his work, a contrastive explanation tool for plans in hybrid domains. Welcome.
Okay, thank you, ma'am. I hope I am audible. So, a very good afternoon to all of you. I am Sajid Sarwar, and I will present our work, a contrastive explanation tool for plans in hybrid. So, this is a collaborative work with Devdan, myself, and Dr. Rajarshi Ray and Dr. Ansuman Banerjee are our supervisor. So, before I delve deeper into this presentation, here is brief outline. First, motivation of our work. Then we work on hybrid systems. So I talk a little about hybrid systems and a planning domain description language, that is PDDL+. I'll show an example planning domain and a planning problem instance, and we'll use it as a reference. Then I'll talk a bit about contrastive explanation. Then I'll present our explanation framework and explain it with an example. And finally, we evaluate our framework and conclude. So we all know that AI planning now been applied in many safety critical real-world application areas. To name a few, like mining, robotics, traffic control, search and rescue missions, etc. And these domains are complex in nature. So plans for these domains are also complex, and such plans need explanation to the end user. So the motivation of XML AI planning is that it should give some sort of explanation about the behavior of an autonomous system to the user to build trust, and this way we can design better transparent system for the user. So I'll explain explainable AI planning with an example. Suppose consider a autonomous car is there, and it navigates a human user to its usual destination, let's say from his residence to his office. And every day the car takes the same route. And what happens if one fine morning, if the car takes a different route without notifying the human user, the user may got terrified why such decision is taken by that system. So principal goal of AI planning is that the AI agent of such autonomous system should give some sort of explanation such that the decision taken by that system is understandable to the user. So for example, the autonomous car should notify that the usual route is congested due to traffic, let's say Bangalore traffic. It's a different problem, all the routes are congested here. So the principal goal here is that the autonomous system should give some sort of explanation so that the decision is understandable. So we work on hybrid systems, and hybrid systems can closely model such real-world scenarios which exhibits mixed and continuous dynamics. So for example, in this figure, there is a simple model of a car. It has only three mode running, running, goal list, and the engine blown. And in these modes, the dynamics of the system continuously evolves, and there is discrete transition between the modes, and we say those are either actions or events. Now, PDDL plus is a planning domain description language that models such type of systems, and it is an extension of PDDL 2.1. The key feature of PDDL plus is that it can handle exogenous events that is not controlled by the environment, as well as it can model the continuous behavior of the system. So a planning instance in PDDL plus is a pair, domain and probe, where domain describes the domain, and the probe is the problem instance where we specify the initial state and the goal configuration of the system. And a plan is, for a planning problem, is a sequence of action that can lead the system from its from its initial state to a goal state. Now we give an example planning domain. In this domain, there is a process moving that basically models the continuous behavior of the system, and it has some discrete transitions as actions. It has 3 actions: accelerate, decelerate, and the stop, and 1 event, that is engine explode. And a planning problem in this domain where we specify the initial condition and the goal condition for that problem instance. Initially the system is in the running mode, and the goal is to reach the goal reach mode within a specified time bound. So when a planning problem is given to a planner, if the planning problem is solvable, planner will generate a plan, and if we execute that plan, that can lead a system from initial state to a desired goal state. So here is in figure 3, here is an example of a plan given by a hybrid system planner, PDL plan, SMT plan plus, and here you can see the sequence of actions that need to be taken in the specific time point to move the system from the initial to the desired goal condition. And here is duration is specifying that all the actions are instantaneous in this domain. So the action applied for the duration is 0 time unit. Now, contrastive explanation is a well-known approach and very popular approach for driving explanation in literature. And the crux of this method is that if we have two alternative plans that moves a system from initial to the same goal state, we always can highlight the contrastness of these two plans to generate explanation. So here is our framework, and this framework can be integrated as a web interface. And in this interface, we have 8 steps. You can see in step 1, in step 1, we are basically choosing the planning domain and a planning problem instance. In step 2, you can choose planners, different planners you can integrate with this interface. So you can choose planners, and when a planner and planning problem is chosen, the planner should provide if the problem is solvable, should provide a plan, and we say that is our original plan, and that will be given to the user. The user observes that plan. Now user may ask some questions about some properties of the plan or some specification of the plan. So in this interface, we have in step 4 some template-sized questions. From there, user can choose a question, and this set of question is not exhaustive, but we believe that it covers many aspects of the plan. And in step 5, user will provide some real parameters, and with these will form a hypothetical model, and that hypothetical model will impose some constraints to the planner such that the hypothetical plan that will be generated, that should adhere the user query. So when we form the hypothetical model, the hypothetical model will given to the planner. Planner will generate an hypothetical plan, and now we have 2 plans. We have an original plan and we have a hypothetical plan. Now we'll compare these 2 plans with some metrics. In our interface, we have just 2 metrics in plan length and plan duration. And with these metrics, we'll generate a contrastive explanation and show the explanation along with the each plan to the user. Now you can see that this process is iterative. So user can ask repeatedly ask question about the plan. We'll cover this topic in later slides. Now here is an example to go through the process. You can choose different planning domain as well as planning problem instance in our interface. We have integrated 2 state-of-the-art hybrid system planner, SMT Plan Plus and NHSP. Now, a plan will be generated, and this is the original plan that will be shown to the user. Now user can, from the drop down menu, there will be some template-sized question will be shown. User can select any of these questions. Let's say it selects a question that is restricting, want to restrict an action to appear before a certain point of time. Now user will provide some real parameters like which action to it want to apply. So here is action, let's say action is disliked, and users want to apply the action before the time point 1. So we form the in the hypothetical model, we extend the original disliked action with some constant, so that if that action apply in a plan, it always appear before the time point 1. And to impose that, we have added some constant in the goal state as well, so that if this appears in the plan, it will always appear before the time point 1. And now you can see a hypothetical plan is generated, and now we can see that that action is now applied in before time point 1. And a hypothetical plan is generated, and we compare the original plan that we have shown earlier and this plan to generate explanation. And here is the explanation that the duration of this plan is longer than the original one. Along with this, we have two more provisions to query a plan with better plan length or better plan duration. In iterative process that we have shown that it harnesses the power of iterative modeling to facilitate user to repeatedly ask question about the plan, and to find a better plan, a plan with better plan length or plan duration, we use the iterative planning with bisection. For example, if user want to know a plan, whether there is a plan with better plan duration, so for that, in the bisection algorithm that we have we have bounds, a lower and upper bound. Initially, we set the lower bound to 0, and the upper bound is the plan duration of the original plan. And in each iteration, we halve this bound and try to find a plan in between, and progressively converge towards a plan that is near optimal.
Sajid, you have 3 more minutes.
Okay. And here is our results. We have 2 domains. We have included 2 benchmark domains for experimenting. We have a card domain and generator domain, and these are the contrastive questions that we have shown. We have 7 questions in the temporalized questions, and we integrated 2 state-of-the-art planner, and these under these planners, the time showing is the mean response time of our interface to generate explanation, and the H model compilation time is showing that to generate the hypothetical model time taken by our interface is shown here. And this is for the finding a plan with better plan duration, and as it is an iterative process, it may take a bit more time. So I like to conclude here. We have provided an interactive user web interface for explaining plans in hybrid systems. We have explored some contrastive questions that the user of the tool may pose, and also shown a framework that can explain those questions. And we propose a iterative remodeling and replanning algorithm for to facilitate user to repeatedly ask question about certain aspect of the plan, as well as finding best competitive plans in that domain, in that area. And our tool provides solution to experiment with different planning domains. So different planning domain can be integrated with this interface, as well as you can plug in different plan generation engine along with the 2 we have shown with this interface. And we demonstrate the results with 2 benchmark domains and 2 state-of-the-art planners. And And the code base of this is already uploaded in the GitHub. So with this, I like to end here. Any questions?
Questions, please? Any questions? So I have one question.
Okay.
So is it like a test case? So you have a goal and your plan will give the steps of execution to reach that goal. So goal means your problem.
No,
Is it
goal
so?
means a planning problem is given, and in that planning problem we have an initial state. Goal is to reach the goal state, and the problem can be solved by the planner. Planner will show that if you need this
So
sequence of
planner means
actions.
steps of execution.
Planner means the plan generation engine that will solve the problem actually.
Thank you. Any other questions? Oh, yeah.
Yeah, do you have anything like a proof of convergence, or you said comparative and contrastive? So do you have any way of measuring whether there's an improvement or a proof of convergence towards an improved parameter?
We like to explain the original plan, whether it is a good plan or not. So proof of whether it is a good plan, in few instances we have seen that a hypothetical plan is not good as the original plan. If some more, other aspects is considered, we can say that a better hypothetical plan can be generated if we added some more constant to the planner or into the planning domain. So better hypothetical plan can be possible. So the goal is here to show to the user that the plan that it observes, in which aspect it can explain the different aspects of that plan.
So they compare it manually.
Yeah.
Yeah, thank you for the question. Thank you, Sajid.
Thank you, ma'am.